All right, so now we're going to talk about how to basically compute the check complex. Okay, and the way you go about doing this is using a sort of smallest enclosing ball. Okay, so we'll describe this algorithm. Okay, so to determine if some subset of points in this full set of points S, right, is in the check complex, right, one needs to check that if sigma is contained in a ball of radius r. Okay. All right. So we're going to call that ball of minimum radius. It's like min ball. Okay. So let min ball of S. I'm sorry, of sigma be the smallest closed ball containing sigma. Okay. Okay, which is unique. So you might ask, well, how do we go about doing this? Yeah, I guess before I say that, it's like, so if the radius of this min ball is less than or equal to r, then sigma will be in the check complex of radius r. Okay, so the radius of min ball is less than or equal to r, right, if and only if sigma is in the check complex of radius r. So the basic idea behind the algorithm is that you have these points, and you're going to try to partition those points into things which are on the boundary of the min ball, and then things which are in the interior. Okay, and so there's going to be sort of a randomized way of going about doing this. And so all you really have to do then is that given the points on the boundary, you need to check, you need to compute the min ball directly, and then the things is like, then you check whether the points in the interior are actually really in the interior as you expected it to be. Okay, so the algorithm is based on the observation that the min ball is determined by this the set of points, the subset of points sorry, the subset of k plus 1 points, and k plus 1 has to be less than or equal to d plus 1, where d is the dimension of the embedding space. Okay, the subset of k plus 1 points that are on the boundary. Okay, all right, so that's the basic idea behind this. And then we take this set of points sigma, and we'll have to find some way of partitioning it into things which we think are going to be interior and things which we think are going to be the exterior. And this is going to be done in a sort of a randomized fashion. Okay? All right, so let's see how, let's write down the algorithm for this. Okay, so we partition sigma, okay, into tau, which is in the interior, new, okay, on the boundary. Okay, and then so to obtain the min ball of sigma, right, we call the following. So we call min ball with sort of sigma and the empty set. Okay, so now I'm going to describe for you. It's like what the algorithm is going to give you. So the algorithm is going to return a ball. The name of the routine is just called min ball, and you put as its inputs, it's like tau and nu. Okay, so tau nu. Okay, so if tau, which if you recall is in the interior, right, is in the empty set, tau is the empty set, then you compute the min ball directly. Because everything is on the boundary, and you know how to do that. Okay, else you do the following. So else you choose a random point. Let's call that u, okay, which is in tau. All right, and I consider a candidate min ball b, which is the min ball. So I'm going to call this recursively, where I essentially remove the point u from tau. So I'm no longer going to put it in the interior, but at the same time I'm not going to put it in the boundary either. Okay, so min ball tau excluding u, and then nu. All right, and then if u is not in this ball, right, then obviously I have a problem, right? So then what I need to do is that b has to be equal to the min ball of tau excluding u, and then I have to put u, it's like on the boundary. Okay, okay, so nu including u. Okay, and then I end this if statement, I end the other if statement, and then I return this ball b. And then the point, of course, is that you know, if you have tau being empty, then you have a set of at most d plus 1 points. Okay, so you're only going to sort of feed it d plus 1 points, basically. Okay, so let me just write a remark here. Right, when tau is empty, right, we have a set of at most d plus 1 points. Okay, all right. So again, it's like the claim is that, you know, if you compute this, if you recursively call this routine in this following way, it's like then you're going to get the min ball. It's like of a given set of points, and then you check the radius of that, and if the radius is less than r, right, or less than equal to r, it's like then that original set of points is going to be in your check complex. All right, so let me stop here for a minute.